Covalent bonds. We'll talk about single bonds first. So when we draw a Lewis structure for a molecular compound with nonmetals, we illustrate this or draw this as the neighboring atoms sharing electrons in a way that will give them octets or duets for hydrogen. Helium is also an exception, but it doesn't make compounds, so we're not going to see it in any of these bonding models. So let's use Lewis structures to show the bonding in water and in chlorine. So let's do water first. I'm going to start with oxygen in the middle. How many valence electrons does oxygen have? 6. 1, 2, 3, 4, 5, 6. And then we've got hydrogen. How many valence electrons does hydrogen have? 1. So hydrogen and oxygen are out there trying to get happy, right? Trying to get 8 valence electrons while hydrogen's trying to get 2. This oxygen's like, hey, hydrogen, give me that electron. I need more electrons so I can have 8. And the hydrogen's like, no way. I want another electron, right? And so they're going to argue, and eventually they're going to share, compromise. So if oxygen shares its electron with hydrogen and hydrogen shares its electron with oxygen, when you share something, it belongs to both of you, right? So let's connect those dots. They're shared between. So hydrogen is going to count both of the shared electrons. My husband and I have 6 children. I have 6 children, he has 6 children, but they're the same children, right? So hydrogen has 2 electrons here. The oxygen has those 2 electrons, but it's the same electrons. Things go, you could, I don't want to go there. Anyway. And so now oxygen's better off. Now it would count itself as having 7, but still not quite. And so it grabs another hydrogen and says, hey, come over here and share with me. And so this hydrogen shares with that oxygen. So now this hydrogen feels like it has 2 electrons, 2 valence electrons. It only has those, though, when it's next to the oxygen and they are sharing. And so this bonds these 2 together. And then the oxygen the oxygen. Thank you. Snickers bonds people together, too. Snickers satisfies. It says so on the label. Must be true. So the oxygen counts all of these electrons as well. And so now it has 2, 4, 6, 8. So we would call these 2 electrons here that are being shared, that's a bonding pair of electrons. And these electrons here being shared between the hydrogen and the oxygen, that's a bonding pair.
Right there, you should do an arrow or something.
Well, it says identify the bonding pairs and the lone pairs. So, I mean, you can kind of choose your way of identifying that. So those 2 electrons up there and these 2 down there are not being shared. They're not involved in a bond. So I've got, they're called lone pairs because they're pairs that are lone. They're not between 2 atoms. So the lone pairs are the blue ones. And the bonding electrons are the green ones. Bonding pairs. So we look at this Lewis structure for water, and we see that oxygen has 2 bonding pairs and 2 lone pairs on it. Each of the hydrogens has 1 bonding pair. Any questions? Let's look at chlorine. So how many valence electrons does chlorine have? 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Is chlorine happy? No. It's almost. Just needs one more electron. So this chlorine says, hey, I need an electron. And this chlorine says, hey, I need an electron too. But I'm not willing to give you mine. Let's share. Chemistry land is a very strange place. When they share, then this chlorine counts all of its lone pairs and the bonding pair. 2, 4, 6, 8. The other chlorine counts the bonding pair and all of its lone pairs. 2, 4, 6, 8. Everybody's happy. Question?
So does that explain why Cl2 is diatomic in the gaseous state?
Yep. This explains why chlorine is a diatomic element. Because chlorine atoms aren't happy. The more scientific explanation, a chlorine atom is higher in energy than a chlorine molecule. Higher in energy is less stable. So these two get together, forming a molecule. Their energy is lowered and they are more stable. So that's going to happen almost all the time. And we'll see a similar thing for the other diatomic elements. Any other questions? Why doesn't, say, neon? Why isn't neon diatomic?
Because it has 8 electrons.
It has 8 valence electrons all by itself. 1, 2, 3, 4, 5, 6, 7, 8. Neon doesn't need to interact with anybody to lower his energy. He's got 8 valence electrons. Why would he screw that up? This is why the noble gases make very, very few compounds. Oh, I guess I should say that these are called single bonds because we're sharing a single pair of electrons. It's a single pair of electrons. And so here I started with dots and then I connected the dots. When we write a Lewis structure, we would typically just use lines instead of dots. So if I do water up here, that's wrong. H, there's a single bond to the oxygen and a single bond to the other hydrogen, and then the lone pairs are on the oxygen. So on this chlorine atom, how many lone pairs are there? This chlorine? 3. 1, 2, 3. Those are the lone pairs, and there's one bonding pair. This other chlorine atom has one bonding pair and 3 lone pairs. Okay, so that was single bonds. You can have atoms that share more than one pair of electrons. So let's look at oxygen. How many valence electrons does oxygen have? 6. So there's one oxygen. 1, 2, 3, 4, 5, 6. There's another one with 6 valence electrons. Neither is happy. So they come together, they're going to share. Hey, I'll share an electron with you. Great, I'll share this one with you. Are they happy? No. They've each got 7 now. Well, let's do more sharing. Now how many?
8.
8. They each have 8. So they got around their little issue by just sharing more. So this is a double bond. I don't know why this guy was so little. Try to make him bigger. So we have a double bond. When you see a line like this, imagine it's got a dot at each end. That's representing a pair of electrons. Oops. Okay, so this oxygen has 2 lone pairs in 2 bonding pairs. So there's 2, 4, 6, 8 electrons, and for this one, 2, 4, 6, 8 octets. Happy. Oxygen's a diatomic molecule because it's more stable that way. It's happier. Okay, nitrogen. Nitrogen has a triple bond. How many valence electrons? 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I'm drawing the dots in that particular order because I know where I'm going with this and I want it to be more convenient. So they can share this one. Are they happy? No. Well, how about that? Happy? Nope. Now? Yeah. Because each of these counts all the electrons in the shared pairs. So 2, 4, 6, 8. 2, 4, 6, 8. That's kind of messy looking. We would normally draw it like this with the 3 lines and then put the dots over here. So each nitrogen has a lone pair of electrons, and then there's a triple bond. Any questions? I love Lewis theory. So we looked at whether our ionic bonding model matched up with reality, and we're going to look at that for the Lewis covalent bonding model also. So water is stable. That's why there's so much water on the earth. It's stable. It just doesn't react with stuff very much. But H3O is unstable. You don't find that naturally occurring. And you could make it, but it's going to react very quickly and go away. There's also 2 other combinations of hydrogen and oxygen, an H3O plus and H2O2. So we're going to look at the Lewis models for these and see what we see. So we already did water, so I'm going to draw that one kind of quick. So there's water. Each hydrogen has a duet, and the oxygen has an octet. Lewis theory predicts that that's a stable molecule. It is a stable molecule. Well, let's look at H3O. You might think, well, let's just start with water and see about adding on an extra hydrogen. So how can we have oxygen share an electron with hydrogen? Well, we could, it's got these lone pairs. It could share 1 electron from its lone pair. This hydrogen's happy now. It's got this single bond, so it's got 2 electrons. How many electrons does the oxygen have now? 9. More is not better. We want exactly 8. So our theory predicts that this is not going to be stable. And it isn't, because you've got 9 electrons on there. So that's not good. What about H3O plus? Well, we'll just save some time. And got H3O. How would we make H3O plus? You gotta take an electron off. So I'll remove this electron. And because it has a charge, I need to put brackets around it and put the charge on the outside. But what does that do to the number of electrons that oxygen has? Brings it back to 8. So do you think this might be stable? Yeah. The theory predicts that it's stable, and it is. Now, it's maybe not as stable as water, but it is found. What about H2O2? We're going to learn how to do this in a minute, but there's the Lewis structure for H2O2, hydrogen peroxide. What do you think? Stable, unstable? Stable, yeah. It's stable. Each hydrogen has 2 electrons. Each oxygen has 8 electrons. Any questions? So covalent bonds, unlike ionic bonds, are highly directional. It's the 2 atoms sharing a pair of electrons between them. If they're not between, then they're not bonding. And so it's a very specific directional bond. The result of this is that covalent compounds have discrete molecules. They have this cluster of atoms that are bonded together, but then between that molecule and the next one, there's very little attraction, unlike the ionic bonds, which go throughout the whole substance. So these weak forces between the molecules give us low melting points. Directional? So a directional bond, so you've got, well, like here in the in water. So this bond is localized. It's in this direction between the oxygen and the hydrogen only. When you have the ionic compounds, you've got sodium and chloride. So there's a force of attraction here, but the sodium's also attracted over here, and down here, and up here, and there's one up on top and there's one behind. And so in lots of directions, the attractions are. Okay? And so that makes it much harder to pull all of this apart because they're attracted all over the place. In a molecular compound like water, the oxygen and this hydrogen, the oxygen and that hydrogen are very strongly attracted to each other. But they are not strongly attracted to anything else. They're just this little unit. They're like very cliquish. And so it's easy to separate these individual molecules from each other.